Who is Jitodev Mukherjee from our section? Jitodev Mukherjee.
Yes, sir. B1 থেকে।
Okay. Okay. Now here, if I apply, say this is my center line, and here we are applying the force P. At any cross section, say here or here or here or at this position, we calculate the average stretch is sigma as P divided by the cross sectional area. Right? We know if the component is subject to say bending moment, so you can calculate the bending stress. If it is subject to torsional moment, you can calculate the torsional stress also. Possible. Now my point is here, say for example, there is one hole at the center, say. Now what will happen when there is a hole in the material? So
Stress concentration.
far from the hole position, at this position, say, at this position or at this position, you may expect the average stress as P divided by the cross-sectional area. Okay, but near, when you will approach nearer to this hole, this value of stress sigma should increase. And what happens here, we may redistribute like this, the stress lines like this. I should use a different color, then it will be easier to understand. It may be like this. Small deviation here. Again, you will get further deviation of the stress lines like this. So these lines are similar to the streamlines you have studied in fluid mechanics. So you may assume like this. Now near the discontinuity, near the hole, the stress value or stress lines are so dense that the stress levels will be higher near the discontinuity of the material, discontinuity of the component. Now this area will be highly dense, and this area is basically under stress concentration. And using the nominal equations, we cannot estimate the amount of stress developed near the discontinuity. So here we introduce the concept of stress concentration. In your drawing class also, you learn how we may reduce the stress concentration in the material. One process you know, by giving fillet radius, we may reduce some effect of stress concentration there. So there are different procedures by which we may reduce the effect of stress concentration. So later on we will study in detail. But right now why we are discussing this thing, near the discontinuity what happens? You take another example, say for example your plate is like this, and here one elliptical hole is present. Like this, okay, and P load is applied. And the dimension is here the major diameter is say 2a and minor diameter say 2b from here to here. This. Now maximum stress may be estimated or approximated like this into 1 plus. So this is the amount of stress or maximum stress may be developed near the discontinuity of the material. Okay. Now you now see if B value tends to 0, what does it mean? There is simple crack like this, which is the position of the crack is perpendicular to the line of action of the force. Then you see sigma max will tend to infinity, right? Now if A value tends to 0, then sigma max maybe it is said 0, this it should be near to sigma. Do you understand this thing or not?
Yes, sir.
Is there any difficulty to understand this thing?
স্যার
Now what
ফর্মুলাটা কিভাবে
happens?
আসছে?
It may be approximated. Later on we will discuss in detail. Okay.
ওকে স্যার।
When we discuss the fatigue loading, at that point we will discuss this thing. Also we will discuss this thing when we will design the component under fracture. Okay. So right now you take this value that the maximum stress near the discontinuity will be like this. Now the thing is, this sigma max tends to infinity. What does it mean? That means when we are applying the force here, near the discontinuity, the material will undergo local plastic deformation. That means if sigma max value tends to infinity, that means it had reached the material locally, the material will fail. You understand? Locally, the material will undergo fracture because we have the fracture stress. If the stress amount is greater than that, then locally the material will undergo that fracture and that crack will propagate, and at the end there should be the separation of this whole component. Now using this conventional procedure we cannot design this type of problem, but line crack is there, one sharp crack is there. But if the crack position here for this type of loading, say one vertical crack is there, then you will get this type of effect. Then that problem is not so high that the material will fail due to local plastic deformation, or locally the material will undergo fracture. Now here we introduce the term design against fracture. So in fracture what happens? The material will undergo local plastic deformation and then the material will undergo local fracture, and that way the crack will propagate and finally the material will fail due to fracture. Okay. Now for crack propagation we have to apply a force. Without any force the crack cannot propagate. So we have to apply some amount of force, and using that force the crack will try to open up, and the crack will open up means locally the material will undergo fracture, then only it is possible to open up the crack at this position. Now there is one equation here. Basically we are trying to define fracture toughness, and how fracture toughness is defined. That's why the small part of the fracture mechanics we are discussing here. Now here we define stress intensity factor. We have one crack. Near the crack, the stress distribution at the crack tip in a particular problem can be estimated. What should be the value? Now I am taking one example like this. In fracture mechanics, we will again discuss this problem, how we are getting these things. Suppose this is one plate. Okay. There is one crack. Like this. Okay. Sorry. Say this is our x-axis. This is y-axis and perpendicular to that is z-axis. And this dimension of this crack is twice a, and I want to take a position of one point, say here, with a distance of r and making an angle of theta. Okay. Now what we can do, I can highlight this portion here later on. I can do like this, say this is my crack tip, is the crack tip position. From here, basically angle is theta, this radius is r. There is one element we have considered, and here sorry, is x, y. So this value should be sigma x, this is sigma y, and this value should be your tau xy. Okay. And for this type of tip, we may estimate the values as sigma x, sigma y, and tau xy. Right now I am writing only the equation. This value is r, so it is 2r under root into cos theta by 2. You may check with any book, 1 minus sin theta by 2 and sin 3 theta by 2. So similarly, sigma y and tau xy, these values may be estimated from this geometry. Okay. Now from here, basically, we try to put sigma x is k by 2 pi r under root 2 pi r into cos theta by 2 into 1 minus sin theta by 2 into sin 3 theta by 2, like this. So basically this is k by root 2 pi r and one function of theta. Okay. Similarly, sigma y may be estimated like this, k by 2 pi r fy of theta, and tau xy 2 pi r f xy theta. Okay. So this way we may estimate that thing. And k is basically here sigma root pi a. this one. And unit should be how much? Unit should be if sigma unit MPa root meter. So that is the unit of this. Now what is this? So this is basically K. This K is called stress intensity factor. What is stress intensity factor? It is the basically, it describes the stress distribution around a crack, around a crack or also a flaw. Now, if there are two cracks with same value of K or stress intensity factor, that means the stress fields are identical, even though the geometries are different. So K is basically the stress intensity factor, and it will describe only the stress distribution around the flaw, around the crack. That is stress intensity factor. Now, taking this stress intensity factor, we can define the fracture toughness. How is it possible? Now, generally in a fracture, there are three modes. One is called, first I draw the figure here. So this is the crack, okay? I hope you may understand the figure, okay? So there is a crack in the component. Now there are three modes. Mode 1. In mode 1, what happens is basically called opening mode, like this. Mode 2, the forces or loadings will be like this. And in mode 3, so if I consider mode 1, the opening mode, the critical value of stress intensity determined in mode 1 is basically, or stress intensity factor in mode 1 will be designated by this K1. The critical value of K1 is basically K1C. Now how this K1C is determined? Now this K1C is basically the fracture toughness, and using which we may design a particular component under fracture. So in mode 1, basically this is opening mode. Mode 2 is basically, you see, shear mode. And mode 3 is basically your outplane shear mode. Now, experimentally what we can do, there are two types of problems. One is called plane stress, and plane stress when sigma zz value should be 0, and one is called plane strain. In plane strain, your epsilon zz should be 0. Anyway, now if we can do the experiment, and if I can calculate K1 value, then we may plot the values here with plate thickness. We are changing the plate thickness there. For different plate thickness, you will get different stress intensity factor in mode 1. So we will try to plot those. Say those values are here like this. Now through this, we'll try to plot the curve, and this curve is generally like this. Now below this, if I increase the plate thickness, even then this K value, K1 value will not change depending on the plate thickness. So this value is basically the critical value of stress intensity factor in mode 1. So if I design the component based on this, then we'll be in safe region and the material should not fail. So this way we can determine the critical value of K1 or Ki, and that value is basically the fracture toughness, and based on that fracture toughness we can design the component under fracture. But the mode is basically opening mode. In other modes you will get different values of fracture toughness. So this is basically one material property. So this material property for fracture is basically fracture toughness. So it is independent of crack length, geometry or loading system. If we try to increase the plate thickness also, your material will give, or the material should not give lower value than K1C for the particular geometry. So it is the material property of the component, and K1C value is basically sigma root pi a, and here if Q1C value is known to you, if I try to design a component based on this, we may calculate what is the critical value of stress we may apply in the material not to open the crack and restriction the opening of the crack. So this sigma c, Q1C is known to me, then we may calculate sigma c value also, the critical value of stress value using this thing. And A here is basically the crack dimension, crack length. So this way we can determine the material property Q1C, and this Q1C is the material property, and using that we can design one component considering fracture of the material. So right now, is it clear that yes, Q1C may be used to design the component under fracture?
ফিজিক্যালি এটা কি বোঝানো হচ্ছে, মানে K1C এর একটা ভ্যালু যদি আমি পাই তাহলে সেটা থেকে আমি
Yes, K1C value is yes. Let me explain again then. K1C value means that if I can calculate K1C value, if the fracture strength, that is sigma root pi a, if I can apply the particular load, and for that load we may calculate the stress intensity factor, right? K1 factor we may calculate. If your stress intensity factor is less than the critical stress intensity factor, then your crack should not propagate. If, depending on the loading amount, your stress intensity factor in mode 1 is more than the critical value of the material fracture toughness, then the material will fail. So we may consider this way. Suppose we have applied sigma x1, sigma y1, And this way, tau x, y1, like this type of loading we have applied. And for this, we may calculate Q1 value, because now we know the equation how to get the stress intensity factor near the crack tip. Now, if I can calculate Q1 value for that particular loading, we'll compare this Q1 with K1C. For our safe design, always K1 should be less than K1C. As the limiting case, it should be less than or equal to K1C. Do you understand up to this?
Yes.
So just like your strength, in our strength, what we have used, we know, say, sigma YT. So in the material, the induced stress, say sigma 1, say, should be less than or equal to sigma YT to make the safe design. We have incorporated factor of safety later on, right? But here, physically, what does it mean? If I apply, say, P amount of load in the material, say this is my material, okay, the stresses will be developed here, and the stress amount developed or induced stress should be less than or equal to the strength of the material, right? If it is brittle material at that time, that should be equal to sigma ut, ultimate point stress. Similar to this, in fracture, what we'll do? We'll try to calculate the stress intensity factor there. And for that material, if I know the critical stress intensity factor, from the laboratory, we may do the experiment, and from there we may get the critical intensity factor of the material, and we may compare these two to make the design. So always your stress intensity factor for that given load should be less than the critical stress intensity factor of the material. Then only we can make one safe design. Do you understand this thing or not?
Yes.
স্যার তার মানে কি মানে
So this is another mode of design. We know based on strength we can design. We know based on rigidity we can make the design. Also using fracture we can make the design. Basically in our last class,
স্যার এটা কি সেম ওই ইন্ডাইরেন্স স্ট্রেসের মতো?
see, for all the cases we have to compare with one material property. For your fatigue loading, yes, we have considered endurance limit there. Based on the endurance limit, we have tried to design the component. In this case, we have to compare with K1C. Understand my point? In static loading, what we have considered? We have considered either yield point stress or your tensile strength of the material, yield strength or tensile strength. Based
Yes.
on rigidity or stiffness, yes, we have calculated the value lateral deflection or angular distortion, and we have compared with the permissible limit. In in fatigue, what we have considered? We have calculated endurance limit of the material, that is a material property, and we are trying to limit our design up to endurance limit. So if we try to design the component, that should be designed below
স্যার
that
আপনার
value.
ভয়েসটা একটু হালকা গ্লিচ করছে কিন্তু
না স্যার
Probably
ঠিক
due to
আছে।
the network. I am taking the class from university, maybe the university internet is not very stable, maybe there may be some problems.
এখন ঠিক আছে স্যার।
Okay, now here also what we will do, we will try to calculate the stress intensity factor. We will get the value of K1 and we will compare that thing with K1C, and from there we will try to get the design, or we can make the design of this material. So we have another separate chapter on this. Right now, basically what is material property, for that purpose only we have defined this thing.
স্যার বলছি এটা কি তখনই ভ্যালিড যখন ম্যাটেরিয়ালটায় কোনো একটা ক্র্যাক হয়ে গেছে, না তার আগেও স্যার এটা ভ্যালিড?
See, if we see minutely in the microstructure also, there are voids, and from there also crack may initiate. Understand? So
Okay, sir.
we can consider any real material with some cracks. So there are discontinuities. You cannot avoid that thing, right? So
Yes,
you may
sir.
design this.
Okay, sir.
Okay. Now another part, probably you have seen. What is this? It is basically the progressive or continuous deformation of a
In high
material,
temperature.
not in high temperature. In high temperature, your creep rate will increase. At constant stress is basically creep. If you increase the temperature, then the effect of creep will be more. So it is temperature dependent. Understand? So if you see, probably you have seen this curve in our presentation. With time, this is a primary mode, secondary, and tertiary. Okay. Here, basically what happens, sorry, this should be one continuous line like this. So this is basically creep curve. So there it is basically strain with time. Okay. And when the load will be applied initially, one strain should be induced in the material. So that is basically epsilon O. Now this type of creep test can be done using constant load or constant stress. Load may be constant, or sometimes we do the test based on constant stress value. So this curve is basically based on constant load. If I change this curve to constant stress, then you may find this curve like this. So this dotted one should be based on constant stress. Now, there are three regions. Primary, where you will get more strain here. Then in this region, your strain is more or less constant, and we try to calculate strain rate, or also the creep rate, we call it minimum creep rate. And based on these, basically, we try to design the material under creep. So in our discussion, when we discuss the material design under creep, at that point, we will discuss all the things and we will try to make the design of the component. Right now, what is creep? What are the regions there? And what are the significance of the regions, and how we can design a component, or in which region we should design the component, why it is not in one, or why it is not in tertiary zone. In zone 2 or secondary zone, we try to maintain the creep, and using a minimum creep rate, we may design the component. So up to this is the material property. Probably we have these materials with our presentation. So is there anything extra in the presentation?
ওই রিজিয়ন গুলো বলা ছিল।
হ্যাঁ, so it is already there.
Yes, sir. Yes.
Okay, you check with that also. So this is basically what you have to do from this. For the examination purpose, what we have to do. So we may answer questions like this. Say like this: what is resilience? What is the importance of this, or how do we measure this resilience property? What is say endurance limit, and what is the significance of endurance limit? How we can measure endurance limit like this? We can ask what is creep and draw the creep curve showing the different regions there. Also, we may ask like this: what is the significance of minimum creep rate in creep curve? Is there any relationship of temperature with the creep of the material? Then we should yes, say yes. If the temperature increases, the creep rate will also increase. So there is a direct relationship of creep with temperature. So this way, here you may prepare short notes on this materials and material properties.
Okay, sir.
Okay. Now what we will study,
স্যার
yes,
বলছি স্যার
yes,
নোটে ক্রিপের ডেফিনেশনে স্যার দেওয়া আছে অ্যাট হাই টেম্পারেচার ক্রিপটা হয়, তাহলে কি স্যার মানে আপনি বলছিলেন টেম্পারেচারের
no,
উপর
no,
ডিপেন্ড?
it may, yes, it is dependent on temperature, but without temperature, at normal temperature, creep may happen. In definition, yes, always we try to relate that temperature. It is true that if we increase the temperature, the effect of creep will be higher. Okay, that is the reason why we put the temperature also in the definition. But without temperature, if you put one component, say for 1 year, 2 years, 5 years, 10 years, then also you may see creep is happening there, though it is kept at room temperature. Understand? So it is possible. But if
Yes,
you
sir.
increase the temperature, creep rate will increase. So always we try to mention the temperature also in the definition, but it does not mean that if the component is kept at room temperature, creep will not happen. Even then, if the item or the component is kept at room temperature, creep may happen. Understand?
sir.
That is
Yes,
why
sir.
that temperature is there in the definition.
ওকে
This
স্যার যে
is
ক্রিপ
material.
কার্ভটা,
Yes.
স্যার যে ক্রিপ কার্ভটা আঁকলেন স্যার, ওটা স্যার মানে নোটটাতে নেই, তো ওই রিজিয়ন গুলো কি ওটা বলে দেবেন?
Okay.
1, 2 or
Again,
3.
basically, why we are not discussing all the things here, because we have one separate chapter on this. We'll
Okay,
design the component based on fatigue. We'll design the component based on fracture. We'll design the component based on creep. So here, basically, why we are discussing this part here, we should know what are the material properties based on which we may design a component. So there are different design procedures. Depending on the problem, we have to choose one, whether it is under fatigue, whether it is under fracture, whether it is under creep. Based on that only, we have to select the appropriate material property to make the design of that component. So here, basically, under material, the first point was properties, right? So that is why we are discussing the different properties of the materials depending on different types of environments, different types of, say, loadings like this.
ওকে স্যার।
Understand?
Yes, sir.
Yes,
Now,
sir.
another part we did not mention earlier. So material is okay. So when we are trying to start one design, we have to select the material. And when we are trying to select the material, we have to consider the properties, different properties of the material, the availability of the material, also cost of the material. Later on, we will discuss material part, the classification of materials. Probably in the next class, probably we will start that thing. But here under processes, there are three types of processes, and how basically these design material processes are related, that is important. If I ask you how these design material processes are related, you should answer it. Now, why processes are important? Because in the processes, what we do, depending on the processes, the properties of the material may be different. So now another thing is, depending on the functions of the component, we may need different surface qualities. We describe by surface roughness, and depending on on surface roughness, the friction and wear properties may vary. So proper functioning of the material, proper functioning of the machine, the processes should be selected at the time of design. So here we call manufacturing aspects in design. Manufacturing aspects in design. Also we call it design for manufacturing and assembly. Okay, design for manufacturing and assembly, and this will help you to simplify the design. Unnecessary machining, say for example, you want to make the machining of the component, and as engineer, your target will be to minimize the machining procedure of the component so that you can avoid the cost, or you can reduce the cost. Also, you can reduce the time to machine the component. So if we can incorporate the design for manufacturing assembly in our design stage, we may simplify the design. Production process time will be less. The cost of the product will be less, or production cost will be less. If we can select the better procedure, then the labor cost will be less. It will decrease assembly procedure also. If we can choose the correct component with correct manufacturing processes, then it may reduce the assembly cost. It will decrease the assembly time. All the things can be addressed at the design stage, because you have to make the component out of the material, and material should be processed. Without that, you cannot make the final product. So at the design stage, we have to think this thing, and this is called basically design for manufacturing and assembly. We have to think how you will manufacture the component and how easily you can assemble the products or assemble the components there to make the final component or final machine. So this is basically the design for manufacturing and assembly. So this is important. This is important in our design also. Now, what are the manufacturing aspects we should consider at the design stage? Now, at the design stage, we have to select the process. The first process, say casting operation of the material. Now, when you try to make the casting operation of the material, what are the parameters you should consider? So in PG level, there is one subject that is called manufacturing aspects in design. So I am sharing the screen here with you. Though there are many points, I am coming to 1 or 2 points there. And from here, you have to write one short note why manufacturing aspects in design is important. And if I ask you, yes, for casting operation, what are the parameters, or what are the important consideration we should consider at the design stage, you should write that. So 3, 4, 5 points should be remembered, and you should prepare one short note on this. Design for manufacturing and assembly. 1 minute. Okay. So first point was here. Probably you can see this thing. So I will not discuss all the things here. Only one point. Say wall thickness and strength of the castings. Now, how the wall thickness of the material may influence the strength of the casting. In one class, probably I mentioned that the cooling rate of the casting may influence the strength of the component. You know, time TTT diagram, time temperature transformation diagram. And from there, you know, if the cooling rate is high, you may expect fine grain structure. And for that fine grain structure, your strength will be more compared to coarse grain structure. Now, if your wall thickness is more, then at the outer surfaces, your cooling rate will be more. At the inner surface, your cooling rate will be less. And the difference in the strength will be high in that case if the wall thickness of the casting is more. Understand? Also, another thing is to give the final shape, to achieve the final product dimension, always we have to remove the material from the outer surfaces. Right? Now, when we are trying to do the machining operation of this cast material or cast component, we have to remove the stronger surfaces or the surfaces with uh, more strength value. Now, there are two disadvantages. One, we are removing the stronger surfaces from the casting. Secondly, by doing this machining operation will increase. So always we have to maintain the optimum wall thickness so that the material can sustain the applied load. Unnecessarily will not increase the wall thickness. Also, at one point also there, for casting operation, minimum wall thickness should be maintained. Otherwise, during the solidification of the material, your wall may break. So generally, we try to maintain the wall thickness more than 6 millimeter, in sometimes 8 millimeter, 10 millimeters, but we have to maintain one minimum wall thickness also. Otherwise, during the casting operation, your wall may break. So wall thickness and strength of casting is related. So you have to maintain that thing when we will consider this casting process, and you have to consider this in design stage only. Understand this point? So
Yes,
here
sir.
you can find this thing, elimination of undercuts. So this figure basically with undercuts. Okay, this is undercuts. Now we have to make the design in a way so that these undercuts can be avoided. You see this figure. Here we have, if design permits, we may change the position of this extended part to this one. Then undercuts are avoided here. You try to simplify the design. You see there are bends. Okay, if it is possible to change it, to simplify the design procedure, to simplify the design here. So if design permits, we'll try to simplify that thing. So at the design stage, if it permits, we can change this design to this design, or it is also more better than this one. Here you see the position of the hole is inclined, but here we have made it horizontal. For this one also, this is unnecessary bend is there, but we try to make like this. Then hydraulic loss here also can be minimized. You know what is hydraulic loss. So here also we can avoid this thing. We can simplify the design. Also we can avoid or we can minimize the hydraulic loss there. So this way there are different points in casting also. So already in the presentation, we have put some points. There are different points Oh, okay, another point I should mention here. 1 minute. Okay, you see this wall. These two walls are there. Now, if I put like this, at this point, what will happen? It is called hotspot. So we will try to eliminate the hotspot. We will try to put the radius here to avoid this hotspot, and we can have a better design there. Probably yes. For this one, you may remember pulley design or pulley drawing. In pulley drawing, we have used probably this type of straight arms, right? Straight arms. But in book also you will find in some cases we have used curved arms.
Yes,
So
sir.
why curved arms are used? Now curved arms are used here, you see, when the material will solidify, at that time it will try to bend. So you should accommodate that phenomena. So we try to make like this. But here, if this arm is a straight arm, what will happen? At this point, the material, as a material property, the material will try to shrink, and there is a possibility that at this position there is a breakage of the arm. So what I will try to do, will try to modify this design to this one to avoid that thing. If we try to maintain this thing, yes, extra material should be provided there, so that the breakage at this position, junction of the arm with the uh, pulley, okay, pulley rim, may be avoided. Okay, so this way you will find different design consideration. There is one full chapter on this manufacturing aspects of casting operation. Yes, prevention of blowholes. You know, in the casting, blowholes is one important parameter. So if there are blowholes, your casting quality will be poor. So we have to avoid the blowholes, so that you have to arrange the pattern in a way, or mold in a way, that the blowholes or entrapped gases can be can come out from the cavity. So we have to arrange the mold in such a way that we can avoid the blowholes. Ribs. These are ribs. Why we use the ribs? By increasing the ribs, basically we are trying to provide more strength and rigidity in the design. So here also we can use different shapes of ribs. Depending on your design, we have to find the appropriate ribs in the casting. So these are the design rules for the ribs only. So there are different points. I know I am not going one by one, but I am trying to mention one, two, 3 points why we should consider this casting operation, or design aspects of the casting operation. Okay. Now coming to say another one, machining operation. You see, what are the rules here? The first rule for machining operation is reduce the length of work surfaces to design minimum required. So you have to consider at the design stage, what should be the machining operation? It is milling, it is turning, it is shaping like this. But for that machining operation, you have to try to reduce the length of the machining, so that easily you can make the component with minimum time. Also, the cost is minimum. So you have to reduce the length of the work surface to design minimum required. Secondly, decrease the machining allowance to the minimum. Manufacture parts by the most productive methods. So if you can go for mass production, it is always better. Yes, easily you can manufacture more parts or more components, and cost of the components will be less. Widely used shape steel roll stock, leaving most of the surfaces in the as roll condition. So if you can take one material with that dimension, and that dimension will be used in the design, then there will be no question of machining. So if it is possible to use the material as it is, then it will be good for you. You may reduce the cost of the product. Make parts from the blanks having their shape as close as possible to their final product. So you can make the product so that you should not go for another type of machining. In different components, we have to do multiple times machining operation. But if it is possible to reduce that machining operation, and using one operation, suppose you can achieve that dimension. So you try to use some blanks, and from there you try to make the component, and your dimension should be as close as to the final dimension. Use composite structure. At one time, you can make say 2-3 components together. If it is possible, then you can go for this, and that will help you to minimize the labor cost. Avoid unnecessary precise machining. So it is not possible to do the machining operation very accurately for all the components. If there is no other functional requirement to get the precise machining operation, then you should not go for this. For bearing, yes, it is true that you have to do say precise machining, but otherwise, if it is not required, you should not go for precision machining operation. If you go for precision machining operation, then time, cost, both will increase. Provide as far as possible for through-pass machining. Now, what is through-pass? In through-pass machining, suppose what happens? Suppose you have this type of extension of this. In one component, this type of extension of the surfaces are like this. This is a cylindrical space. Okay. Now you see the depth of these three or height of these three are different. Now, if it is possible, so here what you have to do after doing this operation, you have to lower the tool position. You have to machining this thing. Then again you have to change the position of the tool. Again you have to do this thing. But if it is possible to maintain, say I am trying to maintain the things here. If design permits, then I will increase the height of the second one and lower this one. And then in one go, we can machine the whole thing. So this is called basically a through-pass machining. So there are different through-pass machining operations, like say broaching. Broaching is one through-pass mass production process, and through-pass machining is possible there. So provide as far as possible through-pass machining. So you may change the design, and if design permits, then you can save your money. If through-pass machining provides impossible, ensure that tool over travel is sufficient to obtain well finished and accurate surface. Say for example, here this through-pass machining is not possible, but your component is here close to this one, then it is very difficult to withdraw the machine from here and also to come at this position. So there should be sufficient gap here to accommodate the tool, and so that you can do the machining operation properly. So there should be a gap, sufficient gap to accommodate that tool. So that is the point we have tried to mention here. If through-pass machining is not possible, ensure that over travel of the tool is sufficient to obtain the well finished and accurate surface. Ensure convenient approach of the cutting tool. the approach of the cutting tool should be such that easily you can fix the position of the cutting tool there to the surface. Make it possible to machine the maximum number of surfaces during one operation. Say for example, there is one hole, there is one say extended surface like this. Now in one operation, say using turning operation, we are using say turning operation, say one turning operation, if we can complete the total requirement of that component, then it will be good. Otherwise you have to detach the component, or you have to take the component from the turning lathe, then you have to go to the other machine. So in this way time will be more, the total time will be more, cost will be more. So there are different points. Okay, so there are different points. All the points will be are pointed there, and you can see the details of this here. But in this class, we will not discuss all the things. Only 4-5 points should be remembered by you, and we have to prepare one short note on this. Yes. Yes, tell me.
লাস্টের ম্যাক্সিমাম ওই ওইটা বুঝতে পারলাম ওই পিপিটিতে।
Now, my point was, say for example, there is one rod like this. Let me take the phone call.
Okay, sir. Okay, sir.
Okay, sir.
Yes. Now, my point was, if it is possible to do the all machining operations or final product from one machine, then it is good. Sometimes it is not possible. Say for example, for your flange of called shaft coupling. Okay. Now, what you have to do process, one is casting process, you have to use casting. Then what you have to do, you have to go for say turning operation to remove the material, to finish the material. Again, you have to go for that is called key cutter. Okay, you have to take the separate operation to make the hole there. Hole there means to accommodate the key, one square key or rectangular key should be accommodated there, and for that you have to make one slot for the key. So there should be at least 3 processes to complete the flange. Now point was, if it is possible to do the things with minimum number of operations, then it is good. For different components, for all the components, it may not be possible, but you may try to reduce the number of operations with 1 or 2 machines. If it is possible to complete or finish the product, then you can minimize the cost, you can minimize the time of the machining. Okay, that was the last point. So this way, in the presentation, you will find for welding also, for forging also. So you may prepare one short note on this. Okay, design
Okay, sir.
for
Okay, sir.
manufacturing and assembly. And there you may consider different processes, mainly you say casting, machining, say your forging, welding, you also know welding operation, say riveting operation, you know riveting operation because in your machine drawing also you have learned it. So this
Yes,
way
sir.
you can put 3-4 points. What are the points we should remember at the time of design? Understand?
Yes, sir.
So
Yes, sir.
in our next class, we will continue from here, probably in the physical mode, right? Please
Yes,
inform
sir.
me when you are coming here, and that way we can start the class here only.
Yes, sir. Asiya will contact you on this matter.
Okay?
Okay, sir.
Okay, sir.
Okay. So
Thank
thank
you,
you
sir.
very much.
Thank you,
Okay.
sir.
Thank you, sir.
Okay. Okay. Thank you.
Thank you, sir.